In this video, we're going to talk about Chapter 9, Curve Fitting. And in particular, we're going to talk about an introduction to curve fitting. So given a set of data in the form xi, yi, where I goes from 1 to n, curve fitting revolves around finding a mathematical model that can describe the relationship y of xi, such that the prediction of the mathematical model would match as closely as possible to the given data. So for example, this shows the black dots as data points, and the blue line is a linear model providing the best linear fit to this data. Another example with the same data, we can fit a cubic model showing here the best cubic fit to this data. So curve fitting is a systematic way to determine the best fit function to the series of data points. So if I have a bunch of data points as shown here, measurement errors and uncertainties cause the points not to fall on a single curve. So curve fitting finds the best fit of the data without necessarily passing exactly through any point. There are two main advantages to finding an appropriate mathematical model with a good fit for the data. The first is reduction of the data. The mathematical model will often have much fewer parameters than the actual data. The second is characterizing the response y of x. So this allows us to calculate y for any value of the variable x within the range of applicability of the model. So curve fitting, which is also called regression, has two main steps. The first step is to assume a particular mathematical model that might fit the data. So for example, we could use a straight line in the form y of x is equal to a naught plus a1x, or a parabolic curve like a naught plus a1x plus a2x squared, or a nonlinear curve such as a naught times a1 to the power negative x. And this is known as the model function or the functional form. The second step then is to find the mathematical model parameters that would result in the best fit with the data. So we do this by minimizing the sum of the squares of the errors between the model prediction and the data. So in this course, we will study several types of regression, including linear regression, where we use a linear mathematical model, and nonlinear regression, where we use a nonlinear mathematical model. Now, it's important to choose an appropriate model for your data. So ideally, the form of the mathematical model should be chosen based on the physics of the problem. So if you know kind of where this data came from and have an understanding of the theory behind the application, then that gives you a good idea of what form the model should take. However, if you don't know anything about the data, you can test different model functions and choose the best one. Some things that you can look for when you're testing different model functions is observing the fit with the trend of the data, observing the relative magnitude of the coefficients. So for example, if you're adding a bunch of terms and you notice one coefficient has a much lower magnitude than the others, then perhaps you could try the model without that coefficient to see if it makes much of a difference. And you can check a plot of the residuals, which is the errors between the model and the data, to see if there are any anomalies or any areas with very large errors that may tell you that your model is not appropriate. And as we will talk about as we go through the linear regression and nonlinear regression, there are methods to calculate the quality of the fit between the model and the data.